Physics chapter 24 theory video 4. So now we are going to deal with forces between currents. Now earlier what we had was there was a single conductor carrying a current and in a magnetic field. Now we are going to talk about two wires conducting currents, and as you know, when the current is passed, there is a magnetic field that is developed around it. So this magnetic field results in an interaction. So that means there has to be, just like the earlier situation, there would be an interaction. So this particular part might be a little bit difficult for you to understand. So listen carefully and read through the explanation. If you find it difficult, then you will be able to understand it better. But still, if you do not understand, then please raise questions, then I can explain it further. Now, in the first circumstance, there are we have to understand it in two different ways. The first one is we have magnetic fields around two current carrying conductors, but they show two unlike currents, that is anti-parallel. So that means one going into the page, the other one flowing out of the page. So as a result, there would be a magnetic field circle around, and at the middle there would be an extra strong field created by both being squashed together, right? Because of this, the wires are going to be pushed apart. They are going to be pushed apart. Now you need to remember the rules. When one goes in, what happens? When one comes out, what happens? So if you use this grip rule and figure out the direction, you would see that it is going to act in this manner, and the force is going to be on either direction. So they are being pushed apart. They are being pushed apart. But if they are like or parallel currents, if they are either both going in or coming out, then they the magnetic fields in the middle get cancelled out. So as a result, the wires get pushed together. The wires get pushed together as shown in the diagram. If you use the motor effect to explain this idea, again we have to look at this diagram, right? In this diagram, I suggest that you look at your diagram on the book. So what happens is, there are two currents I1 and I2, but we talk only about the magnetic field B of one of them, that is I1. The second current is going to flow across the magnetic field of I1. So then what happens is, you can see that B, the magnetic field B is at right angle to I2, right? It is at right angle to I2. So that suggests, right? When it is at right angle, we can use that equation, the BIL force. So using the left hand rule, we can find its direction. Then that will be towards I1. Then if we use the same principle on I1, the force would be in towards I2. As a result, these forces are equal and opposite to one another, right? They would be equal and opposite to one another, and this effect would take place. This effect would take place. I suppose you understand that. they would be attracted towards one another, the two wires. Now we are going to move into practical activity 24.3, but before that let's write down a note on this. Forces between currents. When two conducting wires are considered, the magnetic fields that would be generated as a result of the flow of electricity through them would have an effect on one another. We can figure out the direction of the force using the rules. So obviously you have to first use the grip rule to find out the direction of the field, and after that you have to use the left hand rule to find out the force. You can write that down if you want, and after that write, if two opposite currents within brackets anti-parallel currents or unlike currents, put a dash and write, one going into the book, the other one coming out of the book, the following effect would take place, where a strong magnetic force would be caused at the middle, and this would push the wires apart. However, if like, put a full stop and please draw this first OA diagram before we move on to the other. Draw this diagram, and after drawing that, please write down, if two like or parallel currents are considered, they would have an effect which would cancel out the magnetic field in the middle, and the force would push them towards one another. Leave a line and write. When two currents are shown as below, and if we consider the magnetic field of only one of them, we would be able to understand the effect of the force by using Fleming's left hand rule. Now what we are going to do is we are going to observe this in the laboratory using a practical activity. So here what they do is they use strips of aluminium foil and they mount it so they are parallel and a little distance apart, only a small distance apart. Then we connect them in series with the power supply. As you can see from the top of this, they are using crocodile clips, they are connected in series. So then what we do is we allow a current to occur in both of them. So as the way they are connected, you can see that they have an opposing effect. Anti-parallel currents are going to be there. So then when this happens, you will see that they would bend towards each other or away from each other depending on how the current is going to be used. Now, if it is parallel currents, then it would attract one another. Anti-parallel means they would repel. But don't misunderstand this with opposite poles attracting, and it has nothing to do with this. Here opposite currents would repel one another, right? You can think of it in a simple way by looking at the diagram. The opposite currents repel, but the parallel currents attract. So that is what happens here. So in this particular situation, because they are anti-parallel currents, anti-parallel means they would repel. I hope you understand that. If you understood, I think it would be best if you do the questions. Question number 13. But before that, let's write down a note. The forces between currents can be practically observed using aluminium foil attached in series to a power supply. Depending on whether the current is parallel or anti-parallel, we can see attraction within brackets parallel currents and repulsion anti-parallel currents between the aluminium foils. I hope you understood. If you didn't understand, ask me questions. If you understood, please do question number 13. Now let's move to SI units. Relating SI units. Now we were introduced to an SI unit, that is Tesla. We used to define Tesla using the three other values as well. The ampere, meter and the Newton. So we have to understand how this SI unit relates to each of these things, or how do we derive at Tesla using the other base units. Now there are 7 base units that we have discussed so far. We have met 6 base units. meter, kilogram, second, ampere, Kelvin and mole. The seventh one is the candela, or the unit of luminous intensity. That is something that we will be learning in a different chapter. Now we need to define each of these things using other base units. We can derive at them. We can derive at SI units using the base units. Now, ampere is defined by the magnetic force between two parallel wires carrying a current. Right? So you don't really need to go into the complete basic definition, but you need to have the knowledge that ampere is also a base unit. All the others are derived units. Right? So you have to understand the definition, and from the definition you should be able to derive at whatever the unit that they are asking for. 1 Newton is, you can get it to be 1 kilogram meter per second squared. Right? So you know that acceleration is involved here. Then there is a mass. That mass has to go through a distance of meters. Right? So you can refer it from the equation. That is the amount of power that is needed, amount of force that is needed to accelerate 1 kilogram of substance through a distance of 1 meter, right, is what we refer to as 1 Newton. So that means, so that gives us 1 meters per second squared. So that results in the force, the definition of the force, 1 Newton. So you should be able to derive at a any unit, any derived unit, by using the base units and also by using the definition. I hope you understood this one. So now we learnt about we learned that 1 Newton is equal to 1 kilogram meters per second squared, and then earlier we learned that 1 Tesla is equal to 1 Newton per ampere per meter. So instead of newtons, if we put kilogram meters per second squared, then we will be able to get 1 Tesla is equal to, that meter to meter minus 1 gets cancelled out. Then 1 Tesla is equal to 1 kilogram per ampere per second squared. So then you can actually define, you can interconnect these details. If you have to the formulas that we have learned earlier. Now force is equal to mass into acceleration, F equals ma. Then from that we can figure out acceleration is meters per second squared, mass is kilograms, so Newton can be defined as kilogram meters per second squared. So now these base units and derived units we can figure out using these using the interrelationships between them. That is, if you know the equation, you will be able to use the base units and derive at its final unit. Now meters, base units are meters, kilograms per second, then F equals ma, W equals Fd, P equals E upon T. All of these things, Newton, Joule and Watt, can be defined using those base units and we can derive at them. Then meters, kilograms, second and amperes, Coulomb, Volt and Tesla, because using these equations, Q equals IT, V equals W upon Q and B equals F upon IL. So the deriving at these base units is another very important thing that you need to remember, because that is going to be a part of your questions. Then let's write down a note on that before we go to the final topic relating SI units. Using the base units within brackets m meters, comma kilograms, kg, comma seconds, comma a ampere, comma k Kelvin, comma mole, comma CD, simple C, simple D, within brackets luminous intensity, we can reach derived units which can be deduced from the base units. Example, 1 Newton equals 1 kilogram ms minus 2 kilogram meters per second squared ms minus 2. Because flux density within brackets T, leave a line and write 1T equals 1 Na minus 1 m minus 1. So we substitute, instead of n, we substitute kilogram meters per second squared. Therefore, we get 1T equals 1 kilogram per ampere per second squared. Leave a line and write, using the equations, we can derive at their units using the base units. Please draw this table 24.1. If you have questions, please ask them. Now what we are going to do is we are going to compare the forces in magnetic, electric and gravitational fields. So we have discussed three different types of field: electric, gravitational and magnetic. So now modern theory suggests that electric fields and magnetic fields are a single type of field. We call it electromagnetic field. Gravitational fields are quite different to electromagnetic fields. So that is the reason why we have electromagnetic fields differently and gravitational fields differently. Now you can use gravitational and electrical fields by defining a test mass or a test charge at a point. A test wire, if you place a test wire in a particular point, you can derive at its magnetic field strength also. So we can use the force on a unit mass, force on a unit charge, or force on a unit current. So there would be differences based on the distance that is between masses, then the distance between charges or distance between wires carrying currents. So if the distances are very high, the effects are going to be lesser. This is common for all three. Decreasing strength with distance from the source of the field. So it decreases its strength with distance. They are all represented by field lines, and they all have a direction along the line, and along a single line it is going to be the same. If the field lines are closer together, if the density is higher, that means their relative strength of the field is higher. Now, what kind of forces are generated as a result of these things, or kind of unit forces? if there are forces, if there are two 1 kilogram masses apart, 1 meter apart, they would have a force of attraction between them, which is valued at 6.7 into 10 to the power minus 11 newtons. So you can understand what kind of a high force must be there between sun and the moon. Then if there is a force, if there is a charge of 1 coulomb placed 1 meter away from another charge of 1 coulomb, then there would be a force of 9 into 10 to the power 9 newtons. That is a huge force. One charge of 1 coulomb placed 1 meter apart, that is 9 into 10 to the power 9 newtons. Then the force per meter on 2 wires carrying a current of 1 ampere placed 1 meter apart, that is going to be 2 into 10 to the power minus 7 newtons. So as a result, we can see the gravity is the gravitational force is the weakest, and gravity is the weakest, and the current is the highest. So what we need to understand is electrical forces are the most significant, and for for you can see it is 9 into 10 to the power 9 newtons, 2 charges. So as a result, there is an electrical force. When 2 wires carrying a charge, there would be a magnetic field generated. So that is 2 into 10 to the power minus 7 newtons. Right? But that is in relation to small distances. But when you go very much further, and when there is a huge distance and huge masses involved, then the gravitational field becomes the most significant. For example, planets and in our solar system, planets and the sun and all of these celestial objects, they are kept in place because of these because of the gravitational fields, but the electromagnetic field is comparatively insignificant, right? So it is quite close, very close, it is very high, but further apart they are not very high. So let's write a note on this first and then move on to the summary. Comparing forces, magnetic, electric and gravitational fields. These 3 types of fields share following properties. Number 1, effect in relation to distance between masses, charges or wires carrying currents. Number 2, decreasing strength with distance from the source of the field. That is, further apart they are, the field strength is lesser. Next one, higher the field line density, higher is the strength of the field. The forces, leave a line and write, the forces that they generate can be compared as follows. number 1, gravitational, put a dash and write, the force between two 1 kilogram masses 1 meter apart equals 6.7 into 10 to the power minus 11 newtons. Number 2, a magnetic, the force per meter on two wires carrying a current of 1 ampere placed 1 meter apart equals 2 into 10 to the power minus 7 newtons. Number 3, the force between two charges of 1 coulomb, before you start writing that, electric, the force between two charges of 1 coulomb placed 1 meter apart equals 9 into 10 to the power 9 newtons. Electric, as shown above, electric field strength, electric force is the strongest and gravity is the weakest. While this is true for small distances, when large distances and large objects such as planets are considered, the effect of gravitational field is more significant than the electromagnetic field. I hope you understood. Now let's look at the summary. Moving charges produce a magnetic field, that is electromagnetism. We have different ways of figuring out the direction of the field or the force. Those details you need to know. Then a solenoid or a flat coil would resemble that of a bar magnet, the field lines. Magnetic flux density, B is defined by B equals F of O on IL, where F is the force experienced by the current, I is the current on the conductor, and L is the length of the conductor in magnetic field. Always remember, it is only the part in the magnetic field. Then unit of magnetic flux density is Tesla. 1 T equals 1 Newton per ampere per meter. Then the magnetic force on a current carrying conductor is given by F equals BIL sin theta. If it is 90 degrees, then it becomes 1. So it becomes F equals BIL. We use the force on a current carrying conductor to measure the flux density of a magnetic field. If there are two current carrying conductors, because of their magnetic fields, there would be an interaction, and as a result, there would be a force that would be generated. I hope you understood. If you didn't understand, ask questions. If you understood, please do the exam style questions.